So we want number 2. Which of the following gases will give the most basic solution on dissolving in water? So first of all, we're going to look at H2S. Obviously, it's got the H, so it is an acid. So that's probably not going to be our most basic. NH3, what kind of a substance is NH3? Is it a weak acid, weak base, strong acid, strong base? It is a weak base, yeah. So that might be an option. It's a weak base. We'll see if we have a strong base as well. And then finally, we have a couple of gases. We have CO2 and we have SO2. Whenever you see the O at the end, you're going to remember that you have an oxide. And what do you remember about oxides in terms of acids and bases? Is there anything special about oxides? Yeah, non-metal oxides are acidic. So for example, let's see, non-metal oxide, and again, this is a non-metal. They are acidic. So for example, if we had CO2 and we put it together with H2O, that would give us, we just cram all of those together into one formula. So there's 2 H's, there's 1 C, and there are 3 O's. So we end up with H2CO3. And this particular one causes normal rainwater, just by way of review, to be acidic. Okay, if we have, let's see, if we have SO2, again, it's going to get together with H2O, and you're going to end up with H2SO3, and that is a stronger acid, and it's going to be a contributor to acid rain. There's other things involved in acid rain as well. So in answer to number 2, who is going to have the most basic, that's going to be NH3, which is the only one of them that is a base. Okay, zipping on down to, I think, number 34-ish or something like that. I don't know why I need the sound effects to move, but apparently I do. Okay. We have 30 milliliters of 0.50 molar HCl is titrated with 20 milliliters of 0.50 molar NaOH. What is the pH of the resulting solution? I did this one way last day. I'm going to show you another way of doing it today. Today, what I'm going to do is I'm going to find the millimoles of H+, which is going to be the same as the millimoles of HCl, because it's a 1-to-1 there. So that's going to be 30 milliliters times 0.50 per liter, and that gives us 0.5 times 30. So we have 15 millimoles of H+. Let's find our millimoles of OH minus. So we have 20 milliliters times 0.50 moles per liter, and that gives us 10 millimoles of OH minus. And because H plus and OH minus react in a 1-to-1 fashion, that means that we are going to have who's going to be in excess and by how much. Who is in excess and by how much? Yes, you can just do it the other method. Absolutely. I'm just showing you a different method today just for variety. Okay. Yeah, it's going to be the H plus, and the H plus is in excess by 5 millimoles. The reason I'm showing you this way and not just doing it the other way is that this will work even if they're not the same concentration. Okay, so you would use this method if they weren't the same concentration. So we have H plus, which is 5 millimoles, and it's going to be in a total volume of 50 milliliters. So the concentration of H plus is 5 millimoles over 50 milliliters, and that gives us 0.1 moles per liter, which is equal to 10 to the negative 1 moles per liter. So our pH then equal 1, and I hope that is one of our answers. Let's go take a look. It is B. So you could absolutely do that because they are the same concentration. You could say I have 10 milliliters of the HCl are unreacted. Okay, 10 milliliters of the HCl are unreacted. And so that would mean that we would have 10 milliliters. The new concentration of HCl is equal to our old concentration, 0.50 molar, times our old volume, which the unreacted volume is 10 milliliters, and our new volume is going to be 50 milliliters, and we will still end up with 0.1. Our next question, I think, is number 38. Which of the following will occur when NaF is added to 0.5 molar HF solution? So we're going to have our original solution, HF, in equilibrium with H plus and F minus. And if we're adding NaF, we're really adding sodium ions, which are spectators. And we have fluoride. So what's going to happen is fluoride concentration is going to increase. That's going to cause the system to shift to the left. And as it shifts to the left, then H plus will get used. And so the concentration of H plus is going to go down. And that means that the pH is going to go up. Okay, so we can say, no, the pH is not decreasing. That's wrong. It's not remaining the same. So we're going to have to look at acidity. And if H plus is going down, that means our acidity is decreasing. Okie dokie. And let's take a look. Where were we at now? 46. Okay. What volume? 4.00 times 10 to the minus 2 molar HCl is needed to neutralize 2.00 times 10 to the negative 1 liter. What a weird way to write it. Of 1.00 times 10 to the minus 2 molar LiOH. So HCl is our unknown, because that's the thing we want to find out something about. And that means that LiOH is our known substance. And we are going to use stoichiometry to do this. So we need a balanced equation. Nice simple one here. HCl plus LiOH, 1-to-1 ratio. So what we can do is we can find moles of LiOH, which is our known substance. And then using our balanced equation, the 1-to-1 ratio, we can find moles of HCl, which is our unknown. And then we want to find our liters of HCl. And if we want to find a volume, we will be able to use our molarity because, of course, we can use our moles per liter as a conversion factor. Okay, we might have to write it as liters per mole. And some of you have used a formula last year. I will also show it that way if you prefer. So here we go. We have 2.00 times 10 to the negative 1 liters of LiOH. And we're going to want to find our moles of LiOH because to convert from one substance to another, you always need to find moles. So we need to cancel liters of LiOH and find moles LiOH. And so we are told that we have 1.0 times 10 to the negative 2 molar. Well, remember, molar means moles per liter. So we have 1.00 times 10 to the negative 2 moles of LiOH per liter. We have a 1-to-1 ratio. We end up using 1 HCl for 1 mole lithium hydroxide. So now we have made it to here. And now we need to find our liters of HCl. So we're going to need to cancel our moles of HCl and find our liters of HCl. And the relationship between moles and liters for HCl is the molarity of the HCl, the moles per liter. So we know that we have 4.00 times 10 to the negative 2, and we could rewrite this as moles per liter. And so what that means is we're going to have a 1 liter per 4.00 times 10 to the negative 2 moles. So we have 1 liter per 4.00 times 10 to the negative 2 moles. Okay. So that will give us, let's see, we got a 10 to the negative 2 down here and up here. And so really all we have left is we have 0.2 divided by 4, which is, I'm going to do it on my calculator because otherwise I'm going to put the decimal in the wrong place because that's just how I roll. Divide by 4 equals, there we go, 0.05. And our unit is liters. So let's scroll on up here and see, do we have 0.05 liters? Yes, we do. That would be answer A. Would we like to see the other way of doing that? Anybody? Resounding silence. Okay. All right, number 47, we have a diprotic acid. Oh, it's bolded and underlined. That must be important. A diprotic acid contains how many hydrogens? 2. So we're going to just call that H2A because we don't know its name. Okay. So So we have H2A, and it is reacting with NaOH. And so let's do a balanced equation. H2A plus NaOH gives us, that's going to mean our charge on the A is A2 minus, so we'll have Na2A plus water. And that means we're going to need a 2 right there. Okay. And we needed 0.45 grams of H2A is required. Oh, it required 4.5 times 10 to the minus, did I write H2O and H2A? There we go. 4.5 times 10 to the negative 3 moles. That's not balanced. Oh, right. There we go. Moles of NaOH. So this is how much was needed to neutralize that. And we want to know the mass of 1 mole of the acid. So what we're going to do is we're going to figure out how many moles of H2A is 0.45 grams. And from that, we can figure out how many grams per 1 mole. Okay, so we're going to say we have 4.35 times 10 to the minus 3 moles of NaOH. And we want to find how many moles of H2A we have. We want to cancel moles of NaOH. And our ratio, we go back up, is a 2-to-1 ratio. So 2 there and 1 there. And we get 4.5 times 10 to the minus 3 divided by 2 is 2.25 times 10 to the minus 3 moles of H2A. And that is how many moles weighs 0.45 grams. We don't want the mass of 2.25 times 10 to the minus 3 moles. We want the mass of 1 mole. So we can do like this. We can say, I have 0.45 grams of H2A per 2.25 times 10 to the minus 3 moles. And if I do the division, that's going to give me the mass per 1 mole. That's what doing that division does. So 0.45 divided by 2.25, 10 to the negative 3, and I get 200 grams for 1 mole. You see, it's a ratio thing, right? It's a smaller amount of grams for a smaller amount of moles. We end up with a larger amount of grams for a larger amount of moles. And let's go back up and see if that was correct. Ah, there we go. That's equal to 200 grams, and that's per 1 mole. All right. Where's the next one? Did we want 51? No. 54. There we go. Consider the following equilibrium reaction for the indicator propyl red. If we add NaOH, so of course, if we add NaOH, that means we're adding OH minus. The equilibrium shifts to the, well, OH minus will react with our H3O plus, and we'll end up with water. Okay, 2H2O, but it doesn't matter. For whatever, doesn't matter how many waters we get. Basically what matters is that the OH is reacting with the H3O plus. So our H3O plus concentration is decreasing, which means that our equilibrium is going to shift to the right. And if it's shifting to the right, well, certainly HPR is not increasing. It's going to shift to the right because H3O plus decreases. The way they've phrased it sounds a little strange. They're basically saying it shifts to the right because H3O plus has decreased, would be another way of saying it that might be a little less confusing. Yeah, and that's it. That was number 54. 58. The pH of 0.1 molar Na2SO3 is approximately, okay, you can do some calculations here, or you can look at this and you can say, I have, is this an acid, a base, or a salt? Is Na2S an acid, a base, or a salt? It is a salt. And when you see a salt, you have to ask yourself, what should you be asking yourself about a salt? Hydrolysis, yes. And we know that Na plus does not hydrolyze. However, SO3 minus certainly can. And when your anion hydrolyzes, what kind of solution do you get? You get a basic solution, unless it happens to be amphiprotic and the Ka is greater than the Kb. Unless amphiprotic with Ka greater than Kb. But if you forget that, and it doesn't just come naturally to you, you can just try it out and see. If I put it with water, what can it do? Well, it has no proton to donate, so it has to accept a proton, which means that it's going to become HSO3 plus OH minus. And when we see that OH minus, we can say, yeah, okay, that is a base, okay? So now that we know it's basic, we can rule out pH of 1, we know we can rule out pH of 7. Now our choices are 10 or 14. Now, this is a weak base. It is not those two at the bottom of the table. And if it is a weak base, that means that the concentration of OH minus is going to be less than that original concentration, 0.1 molar. If the concentration of OH was 0.1 molar, that would mean that we had a pH of, a POH of 1, yeah, and that would mean a pH of 13. Since it's less than that, that means it's going to be a pH of 10. If you don't like the math, you can just be like, oh, it's a weak base. Its concentration is sort of like the average concentration that we always give you. What's the chance of it sort of topping out our pH scale? Not very likely with a weak base, not unless you've got it super, super concentrated. Okay? All right, 58. 62 of the following oxides, which will produce the most basic solution. So what do we know about oxides? Yeah, metal oxides are basic. And non-metal oxides are acidic. Okay, so non-metal oxide, non-metal oxide, non-metal oxide, those are all acidic, acidic, acidic. There's our metal oxide, that is our one that is basic. If nobody has any questions, I will just give you your assignment, which is, guess what? The written response on the review. And just to let you know, our class schedule for next week, it is on our calendar. We have meetings then on Tuesday and Friday next week at 9:30. Excellent. I keep waiting for someone to say no second class, but nobody has yet. All right. Remember to let me know if anything goes awry with your life and your schedule or anything like that. And yeah, other than that, have a fine, fine day. A fine day. Thank you for being here so bright and early.